the cloud. Okay, hopefully everyone can still see the slides and we're recording now. What I want to do on the JTD today is originally Dave sort of asked if we could sort of have a bit of a JTD about ZFS and kind of how the I/O path works with ZFS and you know, really related to kind of performance when you're looking at behavior on the file system. You know, how do you understand and trace and figure out what's going on with performance that might be going on here? So what I want to do today is really not give an architecture overview of ZFS or anything like that. This is going to be much more about an introduction, sort of highlighting some of the key components that you would encounter if you're looking at ZFS and try to understand what's happening through the I/O path. And then talk a little bit about some tools that we have that can help you sort of investigate performance issues. But I'm afraid that for a lot of people who already know about ZFS, this is mostly not going to be very useful. So feel free to log off if you don't want to hear this. But for people who do stick around, I'd like to have it be, you know, more interactive. So if people have any feedback or comments on the things as I'm going through, feel free to jump in, or if you have any questions, please go ahead and just jump in. So first, what I'd like to do is kind of talk a little bit about I/O from the logical I/O perspective, which is really what happens when you're doing in your application something like a read or a write. You know, usually when you do a read, for most of the time, that's going to be synchronous. The application isn't going to be able to make further progress until it has the data from the read. You know, there's clearly mechanisms in the system where we can do async I/O, you know, but at the end of the day, whatever needs that data can't make forward progress till it has it. So, you know, for all practical purposes, we just want to think about the synchronous case for read. On the right side, it's a different story. Usually, you can think of that being asynchronous. When an application does a write, you know, it hands that into the kernel, and the kernel basically says, okay, yeah, I got it. But there's really no promise on behalf of the kernel that that data is actually committed to stable storage when you return from that system call. So in a sense, we can think about that as being asynchronous. Now, there clearly is mechanisms in the system that you can use to ensure that the data is actually on stable storage when that write completes. You know, so either when you open the file descriptor, you know, you can specify that you want synchronous for everything. And some applications would do it that way, but a lot of times what happens is you know, you really want to do it more as a transaction, let's say. So you would see this, for example, with something like Postgres, the database we use in Manta, you know, where it's going to do a bunch of writes, let's say, but it's going to treat that as a transaction. So what it does is at the end of a set of writes, it would do an fsync on the file descriptor. And essentially what that says is, don't return back to me until this data is committed to stable storage. So that really is kind of the way that something like Postgres would do, get synchronous semantics, where it knows that the data is stable. So if the system crashes after that, it knows everything is in a good state. So like, for example, I mentioned Postgres as something where we see the fsync used. Another example where we've seen it used in Manta would be like Nginx. When we're saving an object onto the storage server, what Nginx will do is it does the writes of the object, but at the end of that is when it would do an fsync to make sure that the object is committed to stable storage before it's, you know, before the work is acknowledged as being complete. So, you know, that's really kind of the ways that we think about things happening from the logical I/O perspective. So if we want to sort of map that into what's happening in ZFS, you know, a read, you know, kind of goes in, and so what is ZFS doing to, you know, sort of fulfill that. And a key component on the read path in ZFS is what's called the ARC, which is a cache that's in the kernel that essentially is used to try to fulfill the writes without, or the reads, without them having to always go out to disk. So, you know, if you're reading something relatively often, the hope is that would be cached in memory in the kernel, and you know, we don't actually have to do any I/O. And so, depending on the workload, you know, you might see a lot of read activity without hardly any actual I/O going out to the disk. So the key thing, or there's several key things about the ARC that we want to be aware of. You know, it basically expands to use as much of the kernel memory as it can. You know, so what you'll see a lot of times on a system, if you were to look at kernel memory consumption, is you would see a big pool of memory in the kernel that's being used by ZFS, and most of that's being used for the ARC. One of the things that's kind of interesting is when we have a virtual machine, either Beehive or KVM, those actually lock down the memory that they're using for the virtual machine. So they need to actually get memory set aside before they really start up and are running. And so what they have to do is they actually have to put pressure on the ARC to cause it to shrink down so that they can lock that memory down. So that process can sometimes take a while. I think, I don't know if it's, I'm not familiar on the Beehive side, but certainly on KVM, I know we've seen where it takes sometimes maybe several minutes if you're starting up a large virtual machine, where it's putting pressure on the ARC before it can finally get enough memory to lock down to be able to start up. So, you know, the hit rates that we see on the ARC, it totally depends on the workload. Like if we look at a Mantis storage node, for example, we don't see a very good hit rate in the ARC, because a lot of times these objects are sort of being written onto the storage node and then maybe not read back by the user till a month later or something like that. So, you know, we don't see, you know, the hit rates are very low. But, you know, depending on like in JPC, where we do compute loads, you know, with inside zones, we probably do see a pretty good hit rate in the ARC. So it really totally is going to vary there depending on what the workload is. And of course, once that read in ZFS, if it misses the ARC, then of course we have to actually go and do I/O out to the storage to read the data.
Jerry, can you also, they had this in Exenta, can you also dedicate a faster device as an L2, a second level ARC?
You can do L2, but we don't deploy that anywhere.
I know our workloads, it's terrible.
Yeah, so I didn't really mention the L2 ARC because we don't use it anywhere here. But yeah, there is a mechanism to do that, but we don't use it, so I didn't want to get into that too much. But if you see a reference to L2 ARC, yeah, that is a mechanism to do something like that, if you're looking at the code. Okay, so now on the right side, what happens is it's a little bit different. You know, so like I said, you know, essentially an application usually will do the writes, and those kind of go into the kernel, and the kernel says, okay, I got it, I'm going to do that write for you. But the write actually hasn't happened to disk yet. And what ZFS uses is a mechanism which is called transaction groups. And so what it does there is it's actually absorbing the write activity, and it will do that write a little bit later. So you have to kind of be aware about some of the fundamentals of ZFS to understand some of what's going on here. But hopefully everyone knows that ZFS is a copy on write file system. So it's not ever going to be overwriting any blocks on physical storage. It's always going to be allocating new blocks and sort of writing that out in a transaction. So what we always have is we always have a consistent on-disk view of the data when we look at the actual storage. So, you know, there's various things that can be happening when you're doing writes. You know, you can be modifying a block in the middle. You could be appending onto the end of a file. There's metadata that has to be updated to keep track of, free space, file attributes. There's a bunch of things that happen when you're doing writes. And so all of that is kind of getting put together into this transaction group, which is going to be written as an atomic transaction when that transaction group actually goes out to disk. And so usually what's happening on the transaction group is that gets written roughly every 5 seconds. And the system has, it actually sort of keeps 3 different transaction groups going at one time. So there's what's called the open transaction group, which is where the current writes are going into. And then there can be another one that's kind of in a quiescing state where things are settling down, getting ready to write. And then there's finally the syncing state where that transaction group is syncing. So like if you have a transaction group syncing and actually writing that data out to disk, there would be a third transaction group that's open, taking new writes in that would be written to disk a few seconds later. So the key point about these transaction groups when we're thinking about writes is that when an application does writes, you're not going to see any I/O right away. And if you're looking to see something happen on the disk, you won't see that going through because the transaction group is absorbing those writes and they happen a little bit later. So, if you're looking at disk activity and wondering or trying to maybe trace through what's happening, that write actually sort of gets disconnected and handed off into this bigger thing that's happening inside the kernel that's going to do these writes later. So, of course, that's fine for the normal asynchronous writes, the logical asynchronous writes I was talking about. But if you have something that's synchronous, then what happens? And so the other component that ZFS has is what's called the ZIL, or the intent log. And this is essentially a mechanism it uses for handling synchronous writes, which either is because the file was opened for synchronous writes or because you did an fsync. And so, there's a lot of overhead, like I'm alluding to here, that has to happen when a transaction group gets written out. So to deal with that, the ZIL is essentially a log that sort of keeps track of the on-disk information that has to change when a synchronous write happens. And then that gets put onto the disk so that if the system crashes, that log can be replayed back later. But it's not all of the work that would happen with a full transaction group write. So that's the mechanism the system used to sort of deal with synchronous activity in an efficient way, decoupling it from the transaction group. So every data set on the system has a ZIL. And the free space that's in the pool, there's a sort of a mechanism to manage getting free space for these writes without sort of going through all the free space bookkeeping that has to happen on the big transaction group commit. And then once the transaction group is actually committed to the disk, then everything that's in that log can be discarded because now you have everything stable again. And so, normally the ZIL is never read. It's only just written. And it's the only time it has to be read is like when you boot up if there's pending log records because the system crashed, before the latest transaction group was committed. So, that's a little bit of a high-level overview of something of the read and write. And what I want to do is just do a quick aside here for a second. So when you're looking at ZFS, you're going to see that there's a lot of acronyms. And, I've already mentioned the ARC and transaction groups and the ZIL, but there's, once you start diving into the code, you're going to see a whole bunch of other ones. And I've just made a list here. I'm not going to go through all these and explain them in detail. This is more just, you could look at it for reference. Like if you start looking at the code and you see you see these 3-letter acronyms and you're scratching your head and you're thinking, well, how does this relate to the thing I'm looking at? Like, for example, you might see something like the DDT and you think, well, what's that? Well, that's the dedupe table, but we don't ever use dedupe in our use of ZFS. So, you could ignore that, but just knowing what DDT is, you kind of have to hunt down the acronym. If you don't know, you just see it. So this is kind of mostly for reference. But there is probably 3 key things that I do want to talk about a little bit more because they do relate to kind of I/O and how things are working in ZFS, and that's VDEVs, which are virtual devices, the SPA, and ZIOs. So those are three key things that you're going to want to be aware of just as you start diving into ZFS and thinking about I/O. So the VDEV is essentially the concept within ZFS. It's called a virtual device, but it's essentially a representation either of a physical disk or of one of the devices that we build on top of that. So if you look at a Z-pool and ZFS, you're going to see that we're always using redundancy. So there's going to be either a mirror or a concatenation of mirrors to make up the pool, or there's going to be RAID Zs, and those might be concatenated together. So all of that is represented by VDEVs, and it's kind of a hierarchy. So there's a top level, like if you were to look at a Z-pool on a storage node, typically what we have is some, maybe 2 or 3 RAID Z2s concatenated together to make up that Z-pool. And so each one of those RAID Zs is a VDEV, and then they have VDEVs underneath them, that are leaf VDEVs, that are the actual disks that make up that RAID Z. But perhaps if there's a spare that gets pulled into that RAID Z, for example, then there would be an intermediate VDEV. So it's really like a hierarchy of virtual devices. Some of them correspond to physical disks, and others correspond to these higher level things, constructs that we make up, like a RAID Z, for example. The SPA is a key thing you're going to see, and that really relates to the Z-pool itself. So if you normally look at one of our systems, you're only going to see one SPA structure in the kernel, because we really only usually have one Z-pool, which is the zones Z-pool. But there's nothing in ZFS that says you only have to have one. So you usually would never see more than one on our systems, but in theory you could have multiple Z-pools, and each one of those Z-pools would have a SPA structure in the kernel that relates to that Z-pool. And that's where that actually sort of manages the storage and allocates storage for that Z-pool. And so it's the thing that actually holds the VDEVs, for that pool. And then the last thing that's important to sort of know about is a ZIO. So that's sort of the thing that ZFS actually is going to create when I/O has to happen. So like if you do a read and it hits the ARC, normally there's never a ZIO that actually has to go out to disk, as an example. But if we do have to do disk I/O, then what's going to happen is we're going to need a ZIO for that. And so I want to talk about that in a little more detail. So the ZIO is the structure in the system that's going to represent some kind of I/O activity. And this is where it gets actually hard when you're trying to sort of map a logical read, let's say, into something that actually goes, if you're trying to see that flow in the system, it gets hard to do this. And the reason is because it's, first off, it's asynchronous. So when the system decides, okay, you've done a read and I don't have it in the ARC, so I have to go get this off of disk, that read gets handed off to an asynchronous kernel thread. So all of a sudden you're disconnected from the thread that that actually initiated the read at the application level. And it's also one-to-many. So that top level ZIO that gets created in the system, to do that read, is going to fan out almost always. Like on our systems, if you think about, let's say we have a RAID Z that the pool is made up of, the top level ZIO has to turn into ZIOs onto multiple different VDEVs to actually read the different blocks and read the parity so that checksum can happen and everything. So it's not only asynchronous, but it fans out. So it's very difficult to sort of, let's say if you're tracing through the system, and you did a logical read, to turn that into something, it's difficult to see how that turns into the ZIOs that all happen. Now, normally, of course, that isn't too important, because what you're really more interested in is like, how long did my read take, as opposed to not necessarily how long did each one of these ZIOs that actually finally went down down to the different VDEVs and out to disk. You know, most of the time you don't need to see each one of those individually. But you know, but sometimes you might, you know, so that's something to be aware of is that it's going to fan out and it's going to be asynchronous from the thread that actually initiated the call. So, you know, what happens is when these ZIOs go through, there's actually a pipeline that does a bunch of work that has to happen for these, you know, because ZFS sort of has things like compression and checksumming and built in and stuff like that. So there's a whole bunch of work that happens to a ZIO as it's going through this pipeline before it actually goes going out to disk. And this is actually a complicated thing. And what I would actually want people to do if they want to learn about this in more detail, George Wilson gave a really good talk at the OpenZFS meeting that was held a couple months ago, which you can actually watch online. And you know, he takes a lot of time to go through in detail what's happening for these ZIOs as they're working their way through the pipeline. So that would be a good thing to go watch if you're interested in learning more about this. But really, you know, from what I want to talk about today is not the mechanism of the ZIO per se, but kind of what slows this down, right? You know, so if we're thinking about performance and wondering what's happening, what can actually slow things down? So there's several different mechanisms that could get in the way here. And so one of the first things to be aware of is we have what's called the zone throttle. This is something that is specific to Joyent that is not in the upstream ZFS code, but it is in our SmartOS ZFS code. And we built this mechanism 8 years ago, probably now. You know, and the idea of this here is to try to ensure that each zone on the system is getting sort of a fair share of the I/O. So let's see. So if one zone is basically doing all the I/O on the system and the other zones aren't doing much, then that's fine. That zone can do whatever it wants. But let's say there's a bunch of zones that all are trying to do a lot of I/O. What we want to do is we want to make sure that one zone isn't hogging all of the resources and starving the other zones. So I'm not going to explain how this all works today, but if the code has a lot of great comments in it if you want to go look at it. It's the ZFS underbar zone.c source file in the source tree, and it actually explains how the algorithm works and figures out when throttling should happen versus when it's okay to just let I/O run through as fast as it can. So you can read that if you want to understand the algorithms. But that's one component that could be causing I/O to get slow for your zone. And the way this, I mean, one of the things to be aware of is how this actually is configured. So if you look at a zone configuration, there's a property on there called the ZFS IO property. And it actually sort of allows you to set a bit of a priority, which kind of factors into the calculation for what should be done for that zone. You know, so by default, all of our zones are going to have this property set, you know, so this could be, the zone throttle could be taking effect for that zone. But if you set that property to 0 on that zone, then no throttling would ever happen, you know. So we wouldn't normally do this in production for like a customer facing zone, but we might want it to set it to 0. Like if we know that, you know, we're running Postgres on a metadata server in Manta, we really don't want any zone throttling to happen on that zone. So we would want to have that property set to 0. And another thing that can get in the way of I/O is ZFS itself has a write throttle. And the idea of this thing is basically to prevent that writes coming in from sort of taking over too much memory. You know, so if you think about what's happening with that transaction group as writes are coming in, you know, that transaction group, if we didn't do anything, it could potentially just grow really big and use a lot of kernel memory before it actually finally closes and gets written out to disk. So, and we don't want that to happen because it actually leads to a lot of different bad behavior. So ZFS itself can do throttling to slow applications down to sort of keep each transaction group within sort of a manageable size. And it would do that by delaying incoming writes, you know, if it sees that there's a problem. Now, I personally haven't ever observed the ZFS right throttle to actually be a problem. But it's important to be aware that it is there, and so that is a mechanism that could be slowing down writes. There's a couple other things I don't have here on the slide, but maybe I'll just mention real quick that we've seen. So when we do synchronize, when we write the transaction group out to disk, we sync it to disk, we actually have to have space allocated off of the disk to do, we're taking space because it's copy on write. We're writing new blocks now. So we actually have to find free blocks on the disk to use. And so we actually have a ticket. We've been working on this for quite a few months now, OS 7151, where we're seeing in some cases Metaslabs, which is the way ZFS keeps track of free space on disk, where we're seeing the act of loading the data to figure out where free space is can actually cause the write of the transaction group to be slow. So that ticket actually is, we're in the process of figuring that out now. But so just the act of finding free space can actually cause things to get slow. Another thing that's interesting is, if you're doing synchronous writes, the ZIL commit, writing that intent log out to disk, it has to actually be unstable storage before the sync would return. There was actually OS 7314, which Patrick and Brian were working on just recently, identified some problems in that code path, So that actually has been fixed in the upstream ZFS code, but just fixed last week. So none of our platforms probably have that. So that's another area where you can see that like synchronous write activity might be, getting slow because of that problem that was just fixed, but we don't have it yet. So, there's lots of different things, and, these are just some of the things to be aware of about what could get in the way. And there might be new things, or other things that we find in ZFS as we do some different kind of workload, and we kind of just have to dig into the code and try to see what's going on. So that's a really high level, quick overview of some of the pieces of ZFS here. So now if I want to talk a little bit about sort of introducing some monitoring tools real quick. So, what do you use or look at to try to understand what's happening when you're looking for a performance problem? So there's a bunch of command line tools that we have that would be the normal starting point. And of course, there's the usual IO stat, which is maybe the one that everybody would be most familiar with and have used in the past. So in terms of IO stat, I think the key observation I would want to make about that is a lot of times you'll fire that up and you'll look at like the percent busy column, and you'll say, oh, that's 100%. I must be saturating my disk. And I think that would be a mistake to think about that way, because that's not really what percent B means. What it's really saying is it's the percent of the time that there's at least one operation in progress on that disk. So if it's 100%, it means there's always one operation. But modern disks can usually queue up and handle multiple operations at the same time. So you really don't know, is the disk queue full, or am I just keeping like one IO kind of busy all the time out to this disk? So percent B isn't really, I would say, a good indicator that you have saturated disks. It might be, but it might not be. So it might be better when you're looking at IO stat to use the percent W column, the wait time. That might be a better indicator, because what it's really saying is what is the percent of the time that you're waiting for service? So if you see that number going up, higher, then that could be an indication that the queue of operations on the disk itself is full. So that might, you have to just be cautious when you're using IO stat and looking at the numbers, because they don't always mean exactly what you might think they would. So that's just an observation about IO stat. Another tool that I haven't actually found to be that useful, but it does exist, is zpool IO stat. So the zpool command itself can show you IO data about the VDEVs in that pool. because we normally only run with a single Z pool, this isn't that interesting, you know. But if you did have multiple pools, you could actually see like what is the disk activity for a specific pool, which could be interesting. And I don't know, I just haven't found this to be that useful myself, but maybe other people have used that and seen, you know, because you're essentially getting the view from ZFS of like what activity is happening on each of the VDAVs that correspond to the disks that make up the pool. There's the arcstat command, which maybe people have looked at in the past. And that's essentially a command that'll give you information about the arc that I was talking about earlier, the read cache that's in the system. So, you know, that's if you're not sure, like what's my read activity and how is it interacting with the arc, that would be the command that you would want to use. And you could look at, there's a miss % column, you know, so you can actually see like how effective is the arc being for my workload here. Like, am I getting, you know, if the miss % is 90%, then the arc isn't doing too much for you. But, you know, if it's only 10%, then you're getting great hits on the arc. So, you know, you can use that command to look at that. Another command is VFS stat, and this is a Joyent specific command. So we have this in SmartOS, but it doesn't exist in Illumos. And basically, this is a command that we added that allows us to look at the per zone logical I/O that's going on. So, you know, when we have all these different zones and we're trying to figure out like which zones are actually causing more I/O load, you know, you could look at that and actually see. And this is telling you kind of at the VFS level. So it's more of the logical I/O level. You know, what is the read and writes? What's the latency I'm getting? So you can break that down by zone and see what's going on. And this is the command where that I mentioned that that zone throttle. This is where you can actually see how that throttle is impacting your different zones. So it's going to show you things like how much delay is being put onto this zone by the zone throttle, and how much you know, how many times has it been delayed, and what is the time that it's being delayed. So this is the command you can actually use to check if that zone throttle is impacting your workload on different zones. Another one that's also Joyent specific is ZIO stat, and this one is giving you the read operations down at the more at the physical level. And the reason it's only for reads is because, you know, like I said, when the writes go into a transaction group, which get committed later. And so it's very, it's not really even possible to sort of correlate those writes to a particular zone, because all the zones that are doing writes are going into the same transaction group on the file system, and they're all going to get committed out later. You know, so it's the reads that tend to be maybe inducing latency on applications. You know, so you could use ZIO stat to try to understand, like, is the reads, is this application in this zone maybe hitting read latency problems and things like that. So ZIO stat, again, is using as a Joyent specific thing that's using some of the stuff that we've added into the system. So maybe the last command that might be used commonly is the kstat command itself. And this is actually, kstats are the kernel counters that we have, that is actually the source of information for all these other tools that I've listed here. But you can actually look at the raw data, and maybe sometimes that's interesting. So like the zone VFS kstat, that's the actual source of data for the VFS stat command, you know, that we, you know, so you could see it summarized by VFS stat, or you could look at the raw data using the kstat command. One of the things I think that's interesting about that kstat is, you know, there's some information in that kstat that isn't actually exposed through any of the CLIs, but we have this mechanism where we actually quantize operations into different buckets. And this is actually kind of interesting because you can actually see if you were hitting any long latency problems here, either having it ongoing if you compare and look at the difference between one run and the next, or you can just see if you ever hit any ones, you know, because these are just counters that continually count up over time. But it's kind of interesting to look at this if because you can look and you say, oh, look, there was operations here that were in the 10-second bucket. Then you know that you have some kind of I/O problem that needs to further investigation. And in fact, this concept of these buckets is something that Cody's looking at and actually adding this in other parts of the system so we can track some of these long latency operations in other parts of ZFS, like the transaction group syncing and maybe in ZIL commit and things like that. Another case stat is the arc stats. That's the source of information for the arc stat command. If you actually want to look at the raw data, and then the zone ZFS case stat is the source of data for the ZIO, the physical kind of read activity. So that's the source for the ZIO stat command. So those are kind of the command line tools, but if you want to understand a performance issue in a deeper way, then of course you need to dive in and use dtrace and kind of start understanding which part of ZFS is causing you the problem. And so I just want to have a quick example before we wrap up here. This isn't intended to be, like this is the only thing to look at. This is really just an example related to that OS 7151 ticket that I'm in the middle of working on right now. But we're looking at the SPA sync latency and kind of trying to understand why that's slow and correlating it to the metaslabs. I was talking about that a little while ago. So these are just the probes that we can use to do that. And this is a pretty common pattern here that I'm sure everyone is familiar with, where you basically just, take the timestamp and then on entry and exit into the function. And what I'm doing here is I'm L-quantizing that into the bucket so we can kind of see how the latency of the transaction group sync, which is what SPA sync does. That's the transaction group syncing. And then we can see how that relates to metaslab loading, and understand that. And this is kind of, I'm presenting this to you as if it's obvious that this is what you would do, but in fact, this is kind of not, just like we were talking about in the SRE meeting the other day, it takes some iteration and exploration and time before you kind of get to the point where you would understand that these are the two things you would want to look at. So here's an example of doing that on a test machine. And you can see that you can see it's so horrible, in fact, that I had to actually trim out a lot of the rows because it's so bad. But, you can see that there's a case where we actually have, over 100 seconds on writing out a transaction group, which is obviously terrible. But we also can understand why that's happening because we can see that we had to load, let's see, over 170 metaslabs. And we can see that doing that, each one of those took, or at least a lot of them took quite a bit of time. And so we can understand that this is actually, the thing that's causing this transaction group commit to take a long time. So we can actually see these two and understand that that's what's going on. So, you can read more about this if you're interested in looking at the ticket. But, the good news is of course, this is what normal would look like, right? So once we have these metaslabs loaded into memory, and we're doing SPA, this is a 5-minute interval, so we've got 60, which is just what you would about what you would expect when they're going out every 5 seconds. So we can see that things are all normal when metaslabs are loaded, and it's not a problem, and it's only a problem when metaslabs themselves have to be loaded. So this is an example. It's not meant to be, something you would always look at, but really just kind of an example showing how you would use dtrace and then digging into the code to understand a problematic behavior that you're seeing. So that's my last slide. Hopefully, I know we went over on time, but maybe do people have questions or comments or anything that they want to talk about for their own experience in this?
I think the one thing that gets missed in the explanation of the ZIL and the separate rights to the to wherever the permanent location is, is that when you have a synchronous workload, you actually wind up writing things twice. So IO stat's going to show twice as much data written as what your application is actually doing in the worst case, or actually a little bit more than twice, but roughly twice if everything is synchronous and
Yeah, I think that's true. I mean, so you know when you will see sort of strange things like that, where either if you've got a lot of synchronous write, you're going to see the ZIL writes and you're going to see the transaction group writes. And conversely, if you don't have the synchronous, you see a lot less than what you might expect, because everything kind of gets batched up into the transaction group commit. So it's very weird sometimes when you think about writes, because it's kind of going to depend which way it goes, and because of the way things are going in, they can either amplify out or contract down.
Yeah, and they when you're looking to see if the pool is saturated on writes, you can take a look at the IO stat output, and if you find that it's constantly writing, then you're saturated. If not, if you see bursts of writes every 5 seconds, then you're probably okay. I mean, if you have a synchronous write workload that's going at a steady rate but not completely saturated, you can still see steady writes because of the ZIL, but you'll still wind up seeing a bump whenever the transaction group commit comes along every 5 seconds.
Yeah, one thing I don't think I mentioned, I don't remember that I did, is in terms of the ZIL, one of the things that you can do on ZFS is use what's called a slog, or a synchronous log device, which is usually an SSD. And a lot of I don't know that it's on all of our systems, but a lot of our systems, we do use that. So actually those ZIL commits are actually going to go off to a separate device when you have a slog. I mean, you always have a ZIL, but you don't always have a slog. But if you do have a slog, then those ZIL writes will go to that slog, which is an SSD. So they kind of can get decoupled. And you would be able to see then, if you have an SSD slog, you would be able to see the writes going into there and understand, because that would only be used for ZIL commits, understand that that's where that write activity is going to. Anybody else have anything they want to, either questions or comments? Okay, well, I know that I covered a lot of ground. There's probably, in terms of ZFS, there's probably enough material in ZFS where we could do 10 different JTDs on lots of different things. So if people have ideas about more, where they want to dive in more detail on one aspect of ZFS, maybe propose those, and then one of us could put together something specifically on that topic if people are interested.
Once Alex and Jason are through, it would be great to see a ZFS crypto talk from people who've been having their hands in it.
Yeah, that would be a good one for sure. All right, well then I'll go ahead and stop the recording, and thanks everyone.
Thank you, Jerry.